The next measure of relative position or location that we're going to talk about is something called a z-score, okay? A z-score, which is also called a standardized value, okay, is, and you've probably heard this before, and I'll talk about it again in a minute. You've probably heard about standardized scores before, and that's basically what we're talking about. A z-score for a data value X, so for any data value in your data set, the z-score tells you how many standard deviations that your data value is from the mean, okay? And the way we calculate that is using this formula. Now, if you end up with a positive number, it tells you you're that many standard deviations above the mean. And if you get a negative number, it tells you that you're that many standard deviations below or to the left of the mean, okay? Standardizing a data value, it says here, is especially useful when you want to compare data from two or more distributions when their measurement scales are substantially different. Let me give you an example. For example, a lot of times to get into college, some people take, say, the SAT and the ACT, but their measurement scales are very different. For example, on the SAT, you could score a 1450, whereas the ACT ranges, I believe, from like 0 to 36. And so let's say you got a 31 on the ACT, and you want to compare the scores, say applicants with SAT scores versus applicants with ACT scores, and we want to compare them. The way we do that is to standardize those scores, okay? And so we're going to talk about that. It's basically just a rescaling of the scores. So you use a lot of times when things are on different scales, you use z-scores to measure performance. So you can do this, say, if you wanted to look at how a stocks did on the stock market and compare them when they're on different scales. They have different returns and that sort of thing. So again, performance is a key word, you should think about when you're looking at z-scores. But let's go ahead and do some examples so that this makes sense, okay? So let's go here. And we're not going to get to talk too much in detail, but we are going to get a feel for some of this, okay? And you've already seen a little bit of this, and I'll remind you in a little bit. Okay, so here's that same aptitude test data we had talked about before. I don't believe this is exactly accurate, but we're going to pretend this is a standard deviation. Remember, the mean was 63. And it says that Mr. Smith received a score of 83. You remember him from before. Here's his score. And it says, what is his z-score? What is his standardized score? And let's interpret what that value means. Okay, we'll interpret what that means. So what we're going to do, I think you can still see the formula up there. We're going to use this formula right here. So we're going to find his z-score. And his score was an 83. So that's what X stands for. He got an 83. We're going to subtract off the mean of 63 right here, and then divide by the standard deviation, which is 18.54, okay? And what you're going to end up with, and I'm going to do this to 4 decimal places, 866. So there is my answer. When you report your z-score, most people report z-scores to 2 decimal places, okay? But again, it's okay, but we should probably do it to 2. But what does this value mean? Notice that because his z-score is positive, we know that he scored above the mean, which you can actually already see right here. But let's write down what this means. And remember that in general, we want to make sure that we are relating it to the data set when we interpret something, and that we want to do it in context, okay? In plain English. Now, we try not to use what I call statistical jargon or statistical words, but in this case, we can't avoid it completely. Let's talk about this. So, Mr. Smith's test score of 83 is, and now we're going to talk about the z-score, is what? Let's round it to 2 decimals, 1.19. And here's where we can't avoid a little bit of statistical jargon, because what this value measures is the number of standard deviations you are away from the mean. So that's the one word that I can't avoid. Okay, 1.19 standard deviations. I'm writing it as a whole sentence here. And now we got to decide, are we above or below the mean? And in this case, since we got a positive number, we're above. But if we had gotten a negative number, please do not write a negative here. You leave this as a positive number, and the negative is interpreted with the word below. You don't want to put both, because that would be a negative and a negative, which actually makes a positive, right? So it's standard deviations above the teacher average. Above the teacher average. Okay? Is everybody okay with that? I think hopefully you can go over this again. But let's continue with the story. Okay? So he's a teacher that took the test. But now let's say, suppose Mrs. Jones has decided to apply for a job in the school district. Okay? She has taken a different but acceptable aptitude test. Okay? That has a mean of 2,000 and a standard deviation of 200. Now, it's acceptable. Testing usually costs quite a bit of money, so if you have a test that someone's already taken, you don't want to have to retest and spend the money to do that. So she's already taken an acceptable test. It was just on a different scale. She scored a 2,344 on this test, okay? So how can the superintendent compare her to Mr. Smith, for example, or any of the other people, when the average scores and measures are so different for the two tests? Okay, so we have Mrs. Jones. I'm just going to write this down, Mrs. Jones, and remember her scores are on a different scale. So one approach to this, let me write this down, to compare their performance is to standardize the test scores. Now we've already standardized Mr. Smith's test score, so let's go ahead and standardize Mrs. Jones' test score. So what are we going to do? We're going to take her score, which is 2,344, subtract off the mean for her test, which is 2,000, okay, and divide by the standard deviation of 200. And what you're going to get for her test score is 1.72. And you'll notice that she scored 1.72 standard deviations above the teacher average, whereas Mr. Jones only scored 1.19 standard deviations above the average. Notice I've used the word average because most people think of the average as a mean, by the way. And so we're going to use average knowing that it means the mean, even though I told you there's many ways to calculate an average. So it turns out this is not an interpretation, just the fact that Mrs. Jones scored relatively better on her test than Mr. Smith. Okay? Okay. So here we are again comparing that performance. Now what you're going to find is that for a typical sample, you can expect nearly all of the Z-scores. Now remember, every data value in our set has a Z-score. So every value has a Z-score. That means there's going to be 50 Z-scores, okay? Now, for a typical sample, you're going to find that pretty much all of the Z-scores in a sample, not all of them, but pretty much all of them, are going to have Z-scores that lie between -3 and 3. In other words, what that means is that most of your data is going to fall within 3 standard deviations of the mean. Okay, and this is how what's going to help us define an outlier. There's lots of different ways to define this. This is kind of a loose way, but it works. So as a general rule, observations that are more than 3 standard deviations from the mean or have Z-scores that are either less than -3 or bigger than +3 are going to be considered outliers. Remember that we also talked about unusual values. Remember we said that unusual values were going to be more than 2 standard deviations from the mean. Remember we did x bar minus 2s from that rule of thumb, the range rule of thumb, that anything outside of this interval is going to be considered unusual. That's 2 standard deviations from the mean, okay, are the usual values. And then outliers are going to be values that are more than 3 standard deviations from the mean. So instead of the 2, there would be a 3 there. And of course, there'll be some stuff to practice with. So now we have a good definition of what an outlier is. Now we have a good definition of what an outlier is, okay? And then there's a lot to say about z-scores, but this is all we're going to do at this point. Okay, so again, how many standard deviations you are above or below the mean. This is a rescaling that allows you to compare performance, for lack of a better word.